Hello and welcome to these lectures on determinants. Determinants. What determinants are is that they are useful numbers associated with matrices, and the goal of these lectures is to introduce what these numbers are, where they are used, and of course give some idea of the properties so that they can be properly evaluated. So, let me just write down here. So, it is in particular the square matrices that we are going to be talking about, because these numbers, the determinants, are associated with square matrices, and these are some things which we have probably encountered in many contexts, and that is where this usefulness comes. So, let me just look at some examples where these might have been encountered. So, the first example that I want to look at is a linear system of equations. We can have one system of equations as x plus y equal to 10 and 4x equal to y. So, these again come in many contexts. At one level, one can think of them as being equations of two lines, and what we want to do is to solve for their points of intersection. So, these can be So, these are just some illustrations of what these equations may represent from a geometric point of view, and what we want to see is, okay, how do we know what are their points of intersection, whether there is a point of intersection or not, do they intersect at a point. So, this is one area, as we will see, where what we want to define as a determinant is going to play a role. Of course, these equations can also come up in different areas. For example, if we talk about as a school algebra problem, we have some goal to buy some apples and oranges with the constraint that the number of apples and oranges is equal to 10, and that we want to have 4 times as many apples as oranges. So, one could compress that information algebraically into these two equations, saying that x plus y is 10 and that 4x equal to y, and then we want to find the values of x and y. So, here the goal is to solve the system of equations. Okay. So, how do we do this? Well, there are different ways. So, let us try writing them down in a more general format. So, these are the two equations rewritten in a format which suggests that they can be written in a form of a matrix. Right. So, these are just a matrix system of equations. One can imagine that we are looking at a 2-dimensional example, but what we want to do in general is going to also work for an n-dimensional system of equations. More generally, we can talk about this matrix as something like A, B, C, D, where this is the 2 by 2 square matrix, a general form of a 2 by 2 square matrix, which comes naturally in these settings. So, how do we solve these equations? Where do the determinants come up? Let us try to see that. One method of solution is as follows. We can multiply the top equation by d and the bottom one by b and subtract the two. Then what do we get? We get that AD minus BC times x is dm minus bn, okay. And in case AD minus BC, that quantity is not 0, then we could divide both sides by that number. If AD minus BC is not equal to 0, then x is dm minus bn by AD minus BC. So, see, so in a general setting, these are the solution for x. Similarly, we can come up with a solution of y. In that, we write down the equations again. Multiply the top one by C, bottom one by A, and subtract. Okay, and then writing down this is y equal to Cm minus An by Bc minus Ad. Again, this is for the case where this number Ad minus Bc is not 0. So, this is for AD minus BC not 0, because division by 0 is has a lot of issues, not defined for 1. And what we want to say again, going back to the thing, is that if we have a matrix A B C D, a 2 by 2 square matrix A B C D as Mn, then solutions found when AD minus BC is not 0. Now, this quantity AD minus BC is nothing but the determinant of this 2 by 2 matrix. So, this is the determinant. Of the 2 by 2 matrix A, B, C, D. So, this number, which naturally comes up in the context of solving a linear set of equations, we have looked at a 2-dimensional example, it could be a 3-dimensional, 4-dimensional, n-dimensional example, but there is this condition which is nothing but the determinant of the matrix, which is important or which is useful in checking whether the system of equations has a solution or not. So, the problem of existence of solutions can be found by checking the determinant. So, let me just write that down. So, determinant provides a way to check for the existence of solutions in a linear system of equations. Okay. So, through this example, I mean this is sort of the objective of this example, which was to show how a determinant can be a useful way to check for the existence of a solution in the linear system of equations. Perhaps that is the reason why the word determinant comes. I think the root of this word is the verb determine, and that is that it allows us to determine by some calculation, which is nothing but the computation of the determinant, whether the solutions exist or not. Of course, these are just some initial examples. What we are going to do is formally define a determinant, see how they can calculate, but here is just a flavor of these interesting combination of numbers or combination of entries of a matrix which come up in many contexts. And so, the next context which I want to give has a bit more of a geometrical flavor in terms of the area, and there again what we will see is that the determinant plays an important role. So, the next example is a determinant as an area. So, area of what? So, the area is of a parallelogram which depends on the entries of the matrix. So, again let us consider again here a 2 by 2 matrix that we were looking at, and let us try to see how it is related to the area of the columns. So, let us consider these as vectors. So, in the general Cartesian coordinate frame, if I draw these vectors, if I draw one particular illustration of these vectors, let us say this is the vector corresponding to point A C, and this is the vector corresponding to the point B D. Okay, so, these are these two vectors, and now one can think of the parallelogram formed from these vectors as follows. So, this and this point being here as A plus B, C plus D. What I want to state, what I submit is that the area of this parallelogram is nothing but the same quantity that we were checking in the previous example as being non-zero for the existence of solutions, and that is what we should formally define later as the determinant. So, area is nothing but AD minus BC. How does that come? So, let us look at that. So, let me just draw a bigger version of the same figure. A vector here which is AC, a vector here which is BD, and we are trying to enclose it formulate a parallelogram based on those vectors, this point being the sum A plus B and C plus D. Now, we want to find out this area delta, and the way we would like to solve for this is to try to find a bigger area and subtract out the different elements. What I mean is that we can have this dashed area and subtract out from this area the area of this triangle, the area of this rectangle, the area of this triangle, the area of this triangle, the area of this triangle, and then the area of this rectangle. So, what is the overall area of the rectangle, the big rectangle? This is nothing but the length times the breadth, which is A plus B times C plus D. Okay. And from here now we have to calculate the individual area. So, remember that the area of a triangle is half the base and the height, and the area of rectangle as we have just used is the length times the breadth. So, what is the area of this rectangle, this triangle? It is minus half times the base, which is nothing but A, and then the height, which is C. The area of this rectangle, the height is C, and then the length is B minus BC. This triangle, the height is again D, and then the base is B, so minus half BD. Now we move on to this side. The area of this triangle is again minus half. The base here is B and the height is D, minus the area of this rectangle is B and then the height is C, and the area of this triangle, again the base being here, is A and the height is C, minus half AC. So, let us just this expression simplify it. So, delta is A plus B to C plus D, and collecting those expressions we have minus AC minus BD minus 2BC. So, let us simplify this. So, this is AC plus AD plus BC plus BD minus AC minus BD minus 2BC. So, this BD and this BD cancel, one AC cancel, and one of these BC's cancel, leaving us with AD minus BC. So, this AD minus BC term again comes up. Earlier it came up in the context of solving a linear system of equation, a very algebraic context. Here it has come up in a totally different, although related context of trying to find the area of a parallelogram made by the columns of a matrix. In other words, here we have said, okay, we have A, B, C, I think it was the other way around. This was A, B, this was C, this was D, and from here we went to this geometric idea of a parallelogram. And this area, this delta, we have shown is nothing but AD minus BC. So, this number which has now come up in the second context, this is what we are going to call as a determinant. So, this is what goes back to the initial point that we wanted to understand, is that the determinant is a number, and not just any number, it is a useful number. Why is it useful? Because it is helpful in finding out the existence of solutions for a linear system of equations. It is useful in finding out the area of a parallelogram. It has its geometric definition, and there are many such applications of a determinant of a matrix which come up. So, to summarize this, I will just write down that a determinant gives the area of parallelogram formed from the vectors, the column from the columns of a matrix, Just to be mathematically precise, I will just put this area in quotes, because this quantity AD minus BC can be positive or negative depending on the particular values. Area is something we usually think of a positive. So, I mean the relation still holds. We may have to think about the absolute value of the determinant being the actual area, although the sign of the area that we get from these computations may also have some other relevance. But at our level, at this scope, let us just take it that the area of this parallelogram is going to be given by the absolute value of the determinant. Again, as in before, the System of equations was not necessarily constrained to be two-dimensional, although in the example for purposes of illustration we took a two-dimensional system. Similarly here we do not need to just restrict ourselves to the area, we could think of a 3 by 3 square matrix, and in that case it is the volume which is going to be what the determinant or the absolute value of the determinant gives, and we could also think about in the higher dimensional spaces. Okay. So, just for the sake of completeness, let us go back to the initial example that we started with, just as a example of computing the determinant. This was 1 1 4 minus 1 x y. Okay, so this was sort of the 2 by 2 matrix that we generalized into an A B C D matrix, and we did two things. So, let us see whether this system of equations has a solution, and the way to do that would be to calculate the determinant of this matrix. So, what is the determinant of this matrix? So, A D minus B B C. So, 1 into minus 1 minus B, which is 1 into 4. So, this is minus 1 minus 4 is minus 5. So, that is not equal to 0. Therefore, the solution exists. Again, this is a simple example. So, we may think, okay, we could have directly calculated it, but we may imagine that for higher dimensions it may be difficult to explicitly solve for the equations, and in that case the determinant provides a useful way, a quick way to check for the existence of solutions. Similarly, from the point of view of the area, also area is, let us take the absolute value of the determinant is 5. So, this is just taking the absolute value. For the reason that I mentioned, that there is some mathematical meaning to the sign at our level, just let us not worry about it too much, let us just focus on looking at the number that this gives. So, this is sort of completing the circle. We started with this example which comes up either in algebraic context or in trying to find the intersection of points of lines, and what we see formulating it in terms of a matrix problem, the solution or the resolution of what we want to do hinges on checking the value of a number or computing this number AD minus BC for a 2 by 2 square matrix, which is nothing but a determinant of it. So, therefore, this determinant is a useful important number. So, going back to what we want to do. So, let us say determinants. Rather than writing this one of the longer words, determinants, we will use notation either DET, determinant of A, or simply we will just put it in these two vertical lines, and we will note that this A is a square matrix. And what we want to do is three things. First, we want to, having already seen, so what we have done so far has just been trying to motivate the need for a determinant in these two different contexts. What we want to do is to first formally define a determinant. So, we will define a determinant. That is, formally come up with a procedure to calculate the determinant for a general n by n matrix, although we will be using it mostly for 2 by 2 or 3 by 3 matrices. A 1 by 1 matrix is essentially just a number, so that determinant is equal to the value of the number. After defining a determinant, we will look at some ways in which one could calculate the determinant. So, there may be one method, the definition provides one way to calculate the determinant, but what we will see are a set of properties which allow us to manipulate the determinant in such a way that it becomes easier to calculate. So, that is the other thing that we will see, that is the number 2 properties. And finally, what we are going to do is to look at some more of the applications of determinants of a similar line to what we just see, that it helps us to find the existence of solutions, it finds the areas and some other things. So, we will look at how where we can apply the power of this simple number. So, this then is the outline of these set of lectures. All right. So, let us start by defining a determinant. Just to make sure our notations are clear, I will start by writing down a general matrix A and then see what are the sub elements, sub definitions which need to be made before finally coming up with the definition of the determinant. So, A is a general square matrix, let us say an n by n square matrix, and also write it in this representation where Aij represents the ith row and jth column. So, ith row, jth column, or if we try to write down the matrix as a whole, this would be something like A11 because it is the first row and the first column, then A12 first row second column, so on, then the first row nth column, next row A21 second row first column, A22 second row second column, so on, second row nth column, and likewise we will have the nth row first column, nth row second column, and then the final one nth row nth column. So, this is writing down the matrix in its full detail, or we could also just think of it writing the ith row, jth column. So, column j, row I, and this entry is Aij. Right. So, this is a general n by n matrix. We have already seen an example of a 2 by 2 matrix, and what we want to do is to say, okay, how do we now, goal is to say, okay, what is the determinant of A? So, goal, what is the determinant of A in terms of Aij? So, for that, what we want to do first is we have to define what is called as a minor. So, a minor is a quantity which is associated with each entry. So, minor Mij is associated with each entry, okay. And how is the minor defined? It is defined by a determinant of the matrix obtained by deleting the ith row and the jth column. So, if you have a matrix which has entries Aij, if you delete the jth column and the ith row, we are remaining by another square matrix which is now of dimension n minus 1. A minor is nothing but the determinant of that matrix. It is the determinant of a matrix obtained from A after deleting the ith row and jth column. For example, let us look at an example, again this matrix that we are familiar with. Suppose A was a 2 by 2 matrix that we had encountered previously, 1 1 4 minus 1. Okay. So this is A11, this is A12, this is A21, and this is A22. So what is the minor of A12, i.e. that is M12? M12 is nothing but the determinant of a matrix obtained by deleting the first row and the second column. So we will delete the first row, this one, and then we will delete this second column, and so M12 is nothing but the determinant of the matrix which has a single element 4, which, as we have said before, is nothing but 4. So we are going to say that the determinant of a scalar number is always the same scalar. So the minor is 4, as we take determinant of scalar as itself. Okay, so this is the definition of a minor, and then closely related to the definition of a minor is this idea of a cofactor. So cofactor, just like the minor, it is also associated with each element of a matrix. So we call it, denote it as Aij, and the cofactor is equal in magnitude to the minor, but it can have a different sign, and the sign will depend on the value of the row I and the value of the column j index. So this cofactor is defined as Aij is minus 1 power I plus j into Mij. So it is this power of minus 1 depending on whether I plus j is even or odd, which will determine whether the cofactor is equal to the minor or it is equal to minus times the minor. So in the previous example, what would be the cofactor? A12 is going to be minus 1 power 1 plus 2 into M12, which is minus 1 cube M12, and minus 1 cube is minus 1. So this is minus M12, and since M12 was 4, this is minus 4. So the cofactor, this is an example of a cofactor calculation, and we will do some more examples of this to define, to say what. So eventually we want to define a determinant, which is the next step, but before that we need these sub elements of minor and cofactor. Now we may think, okay, why do we need to define so many things? Already we know for a 2 by 2 matrix is AD minus BC, for a matrix ABCD, for a general 3 by 3, for a general n by n, why don't we define it like that? The reason is that we want like a simple scalable way to define a determinant for elegance with the elegant notation, which for it to be easy to represent in a simplified manner. So with these definitions of the minor and the cofactor, we can now define the determinant. So determinant is the sum of the product of elements of a row or a column with their corresponding cofactors. Okay. So, what we mean here, let us just go through this. What we are saying is that the determinant is the sum of a product, and the sum contains, basically the sum contains individual elements which are products. What are these products? These are products of the elements of a matrix, so one row or one column, and they are products of that element with their corresponding cofactors. So, their corresponding cofactors. So, mathematically we would say that the determinant of A is the summation over I of Aij times Aij for a fixed j. So, we may either fix a column and sum over the rows, or we could fix a row and sum over the column, any column. So, or this is equal to the summation of j Aij for fixed I. So, that is how we define a determinant. Okay. So, many things we have possibilities to do. I think the one thing, or the first thing that we should do is to go back and check whether for a 2 by 2 matrix A, B, C, D, the determinant that we get from this definition is whether it is equal to AD minus BC or not, whether we can derive that. Then how do we come up with a determinant for a higher dimensional matrix? That is the other thing that we need to see. And of course, the thing that we have taken is that the determinant of a scalar, which is nothing but a 1 by 1 matrix, is itself. So, the examples that we can consider now are, so 1 by 1 determinant, apologies, so 1 by 1 matrix which is a scalar, its determinant was taken as the scalar itself. Okay. So, 1 by 1 matrix anyway is a scalar, its determinant is a scalar itself. Next, 2 by 2 matrix, let us see what it comes out to. So, we have already worked with a 2 by 2 matrix, but now let us do it in a formal rigorous setting. So, here let us start by expanding along this row. Okay. So, what we need to do is to write down this as A times the cofactor of A. So, what is the cofactor of A? Cofactor of the element A is nothing but the matrix or the determinant of the matrix which comes after deleting the row and the column of which A is part of. So, essentially just the element D, because if you cancel this row and this column, we are left with D, but times minus 1 power the sum of the row index and column index of A. So, the row index of A is 1 and the column index of A is also 1. So, this is going to be minus 1, 1 plus 1. So, minus 1 square. So, this is nothing but D itself. So, this is over here D. Similarly, when we expand in terms of this row, so we have AD, and then the next term in the sum is the product of B, the element B and its corresponding cofactor. So, this is plus B times the cofactor of B. So, what is the cofactor of B? Cofactor of B is the determinant of the matrix which comes after deleting the row and the column of that B belongs to, and so that is nothing but C, but it is multiplied by minus 1 power the sum of the row and column index of B. So, if you see B belongs to the first row, but second column. So, this is minus 1 power 1 plus 2. So, minus 1 cube. So, it is minus C. So, this number goes over here. So, all in all, the determinant of this matrix is going to be AD minus BC, because it is this minus C which comes over here. So, again we are go back to our expression which we have seen multiple times, which is AD minus BC. We could also expand along. So, here we expanded along this row. We could check by expanding along this row or this column what happens. So, let us do one of them. Let us expand along another column. The reason for doing this is because the determinant definition, the way we have said it, is that it can either expand along a row, in fact any row, but it has to be one row, and it can also expand around a column, any column, but it has to be one column. So, let us try to check that by expanding along a different column and seeing whether we recover the same number or not. So, here is the matrix A, B, C, D, and let us expand along this. As before, what we have to do is to say, okay, it is a sum of a product. The first product term is going to be B times its cofactor plus A times its cofactor. So, again, what is the cofactor of B? That does not change whether we expand along a row or a column, that we already calculated previously to be minus C. Okay. So, since we are expanding along this column, this entry should actually be D and not A. And what we need to multiply with this D is its corresponding cofactor. So, we have not calculated the cofactor of D before. In the previous page we calculated the cofactor of A and B, but now I think for a 2 by 2 matrix it is relatively straightforward to calculate the cofactor. So, just imagine blanking out the column that D belongs to. So, no B and no D, and also the row that D belongs to. So, no C. So, what we are left with is just A. So, that is what we are multiplying D by, and as we see, this wonderful expression comes out to be again AD minus BC, which is the same as before. So, this is a good sanity check, a good consistency check that we see. So, I think if nothing else, one of the things which should stay back from this lecture is just this quantity AD minus BC, which is related to a square matrix ABCD. So, what we have seen is how this comes up through the formal definition of the matrix determinant, and also even if you do not consider the determinant definition explicitly, when we try to solve like a 2-dimensional system of equations, and again it is the determinant of the associated matrix which tells us whether the solutions may exist or not. Or if you look at geometrically the area of a parallelogram formed by the columns of the matrix, then this number tells us the area. So, this is in a sense a very magical number to have. So, we have seen this in multiple contexts. We have seen this as formal definition of determinant. We have seen this as a way number to check existence of solutions, and we have also seen this number as area of parallelogram. All right. The next thing to do is to now look at a 3 by 3 matrix. In principle, we have already defined the determinant for a general matrix, n by n matrix. So, in a sense we should already know how to calculate it, but there is a lot of merit in actually looking at specific examples and making the calculation. So, let us look at a 3 by 3 matrix, and in this case let us take a numerical example. So, the 3 by 3 matrix that we have here has the entries 1, 0, 2, 3, minus 1, 2, 5, 2 and 0. So, the question here is, what is the determinant? So, how will we calculate the determinant? What we have to do is pick any row or column. Looking at the matrix, for reasons of calculations, we always want to do the less amount of work or the more efficient amount of work. So, as you see here, there are 3 rows, 3 columns, in principle 9 choices, but one row and one column have 1 0 in them. So, that automatically tells us that the entry is 0. So, you can multiply it with whatever is its cofactor, that term is going to be 0. So, we do not need to calculate the cofactor. So, we can get away by calculating just 2 cofactors if we expand either along the first row or the third column. So, let us now expand along the first row. So, we have 1 times the cofactor. So, cofactor is going to be minus 1 power 1 plus 1 times the determinant of the matrix obtained by deleting the first row and the first column. So, that is minus 1, 2, 2, 0. Then there is going to be the third term, the second term in the sum, apologies, is going to be 0. Now, we do not really care what the cofactor is because it is multiplied by 0. So, it is going to be 0, and then the third term is going to be 2, which is this entry. We are expanding along this column, this row, apologies. So, this is going to be 2 times minus 1 power the first row and the third column times the determinant obtained by deleting the first row and this column. So, 3 minus 1, 5, 2. So, this term is already 0. So, this determinant is going to be minus 1 square. So, 1 times this determinant. Now, we know we have done these 2 by 2 determinant calculations many times. So, now we can just say, okay, this is A, B, C, D. So, determinant of this is going to be A D minus B C. So, minus 1 into 0 minus 2 into 2 times here. So, plus 2 and minus 1 power 4 is 1, again a 2 by 2 determinant. So, we say 3 into 2 minus 1 into 5. So, this is 0. So, here we get minus 4 plus 2 times 6, and then this is 5. So, this is 11 times 2, 22 minus 4. So, minus 4 plus 22, which is equal to 80. So, this is the value or how we can compute the determinant for a numerical example. All right. So, this is a good point to summarize what we have done in this lecture. So, we have talked about determinants, all right, and we talked about defining a determinant, so in this we start by noting that determinant of a scalar is the scalar itself, and then from there move on to defining a 2 by 2, 3 by 3 and a general n by n determinant through the calculation of the elements, minors and cofactors. And before that we looked at some places where these determinants arise. So, these arise in many contexts, such as consistency or finding out whether solutions exist, exist and in computing areas I mean these are some places where they arise, and I think historically these have been used for these and perhaps many other contexts almost since the 1600s or so. You can imagine that the ideas of calculating the areas, in finding out whether there are systems of linear equations, what are the solutions, whether they exist or not, like finding out the intersections of lines. These have problems which have been thought about for many years, and what is very interesting is that the calculation of these determinants, the use of these determinants continues to the present age. There are many areas in engineering, in science, where the idea of calculating the determinants and then the higher level advanced concepts around the calculation of determinants are very useful. So, that is what we hope to cover in the next lecture, is to look at some properties of the determinants which enable many of these applications. So, next we will look at the properties. In their evaluation. So, we aim to look at properties of determinants which will help in their evaluation. So, this is sort of the program for the next time. We will look at the properties of the determinants, and thank you for your attention, and look forward to look at the other aspects of the determinants in the coming lectures.